They called it the Devil's Engine, a machine so violent, so unpredictable that it could shatter windows 3 blocks away. One that didn't need fuel, didn't need fire, just 2 simple liquids that became deadly when they met. This was the Sprengel Explosive Engine, born in the 1870s from the mind of a man obsessed with power. Not the kind you plug into a wall, but the kind that could level buildings. Hermann Sprengel didn't set out to create a monster. He wanted to revolutionize how we think about energy itself. What he built instead was something that terrified even him. The year was 1873. Steam engines ruled the world, belching smoke and demanding constant feeding with coal and water. But Hermann Sprengel saw their weakness. They were slaves to combustion, dependent on fire, limited by the very materials they burned. What if there was another way? What if power could come not from burning, but from something far more immediate, far more violent? That question would lead him down a path that changed everything we thought we knew about engines. Sprengel wasn't your typical inventor. He was a chemist first, an engineer second. Where others saw limitations, he saw chemistry waiting to be unleashed. His breakthrough came when he realized that explosion didn't need to happen in a furnace. It could happen in a cylinder, controlled, directed, harnessed. The concept was beautiful in its simplicity and terrifying in its potential. 2 liquids perfectly harmless apart, but when combined in the right proportions at the right moment, they would detonate with a force that made gunpowder look like a firecracker. The heart of Sprengel's engine was deceptively simple. 2 separate chambers, 2 different liquids. In one chamber, concentrated nitric acid. In the other, a mixture of benzene and toluene. Neither dangerous on their own, but together they formed what would become known as Sprengel Explosive. When these liquids mixed in the engine cylinder, they didn't just burn. They exploded. The explosion drove a piston with such force that it could generate more power per stroke than any steam engine of the time. No boiler needed, no coal required, no waiting for pressure to build. Just pure, instantaneous chemical violence converted into mechanical motion. But this wasn't just about mixing chemicals and hoping for the best. Sprengel had to solve problems that no engineer had ever faced before. How do you time an explosion? How do you control something that wants to destroy everything around it? How do you make sure the machine doesn't tear itself apart with its own power? The timing mechanism was perhaps his greatest achievement. A precisely calibrated valve system that would inject the exact amounts of each liquid at the exact moment needed. Too early and the explosion would happen outside the cylinder. Too late, and there would be no explosion at all. The margin for error was measured in fractions of a second. The engine's first public demonstration was unlike anything the world had seen. No smoke, no steam, no gradual buildup of power. Just a series of controlled explosions that made the ground shake and the air itself seem to crack. Witnesses described it as watching lightning being born inside a machine. The sound wasn't the steady chug of a steam engine. It was a rhythmic thunder, each stroke announcing itself with a violence that made grown men step back. The power output was staggering. Where a steam engine might produce 20 horsepower, Sprengel's machine could generate over 100 from a much smaller package. But power came with a price. The engine was incredibly dangerous to operate. One mistake in the mixture, one failure in the timing, and the entire machine could explode. Early operators learned to work the engine from a distance using long poles to manipulate the controls. The acid would eat through metal parts, requiring constant replacement. The explosive mixture would sometimes detonate prematurely, sending shrapnel flying. Several prototype engines literally blew themselves apart during testing, leaving nothing but twisted metal and chemical stains on the ground. The chemistry behind the engine was both elegant and terrifying. Nitric acid, a powerful oxidizer, would react with the hydrocarbon mixture to create a rapid oxidation reaction. But this wasn't the slow, controlled burn of coal or wood. This was a detonation, a chemical reaction that propagated faster than the speed of sound. The explosion would create temperatures of over 3,000 degrees Celsius in milliseconds, generating pressures that could exceed 1,000 pounds per square inch. That pressure, properly harnessed, could drive pistons with incredible force. What made Sprengel's engine revolutionary wasn't just its power, but its efficiency. Steam engines wasted enormous amounts of energy heating water, maintaining pressure, and dealing with the inefficiencies of external combustion. The Sprengel engine eliminated all of that. Every drop of chemical fuel was converted directly into mechanical energy. No heat lost to the atmosphere, no energy wasted on maintaining steam pressure. It was internal combustion taken to its logical extreme. The engine caught the attention of military engineers almost immediately. Here was a power source that could be incredibly compact yet incredibly powerful. Naval architects began designing warships around Sprengel engines, imagining vessels that could outrun and outgun anything on the seas. The German military was particularly interested, seeing the potential for mobile artillery and rapid deployment systems. But the engine's volatility made it almost impossible to use in combat conditions. The slightest damage to the fuel system could turn the engine into a bomb. Industrial applications seemed more promising. Factories could use Sprengel engines to power machinery without the massive boiler rooms required by steam. Mining operations could use portable versions to power equipment deep underground where coal smoke would be deadly. The engine's ability to start instantly without the lengthy warm-up time of steam made it ideal for emergency power applications. Several power stations were built around large Sprengel engines, providing electricity to entire city blocks. The fuel system was a marvel of precision engineering. The nitric acid had to be stored in specially lined containers that could resist its corrosive properties. The hydrocarbon mixture required careful temperature control to prevent premature reactions. The injection system used a series of precisely machined valves that could meter exact amounts of each component. The entire fuel delivery system was essentially a chemical laboratory built into a machine, requiring operators who were as much chemist as engineer. Safety protocols for Sprengel engines were unlike anything developed for previous power sources. Operators wore protective clothing that could resist acid burns. Emergency neutralizing agents were kept nearby to deal with spills. The engine buildings were constructed with blowout panels that could direct explosions away from populated areas. Despite these precautions, accidents were common. Several engine houses were completely destroyed by runaway reactions, and the insurance industry began charging premium rates for any facility housing a Sprengel engine. The engine's influence on engineering thinking was profound. It demonstrated that internal combustion could be far more efficient than external combustion. It showed that chemical energy could be converted directly into mechanical work without the intermediate step of heating water. These concepts would eventually influence the development of the internal combustion engines that would power automobiles and aircraft. But Sprengel's engine was too powerful, too dangerous, too uncontrollable for widespread adoption. By the 1880s, the limitations of the Sprengel engine had become clear. The corrosive nature of the fuel system meant constant maintenance and replacement of parts. The explosive power that made it so effective also made it incredibly dangerous to operate. The specialized knowledge required to run the engine safely meant that skilled operators were rare and expensive. Most critically, the engine's tendency to destroy itself meant that operating costs were often higher than the value of the power it produced. But the story of the Sprengel engine didn't end with its commercial failure. Military researchers continued to study its principles, leading to developments in explosive technology and chemical engineering. The precision injection systems developed for the engine influenced the design of fuel injection systems for later internal combustion engines. The safety protocols developed for handling the engine's dangerous chemicals became the foundation for industrial chemical safety standards. The engine also captured the imagination of science fiction writers and futurists. Here was a machine that seemed to harness the very forces of destruction for constructive purposes. Stories of Sprengel engines powering fantastic machines appeared in the popular press. Jules Verne referenced similar concepts in his novels, imagining vessels powered by controlled explosions traveling to the moon and the depths of the ocean. The engine became a symbol of humanity's ability to harness nature's most violent forces. Today, the principles behind the Sprengel engine live on in modern technology. Rocket engines use similar concepts, mixing fuel and oxidizer to create controlled explosions that propel spacecraft. Industrial explosives still use variations of Sprengel's chemical combinations. The precision timing and fuel injection systems pioneered for the engine influenced the development of modern automotive engines. Even the safety protocols developed for handling the engine's dangerous chemicals continue to influence industrial safety standards. The Sprengel Explosive Engine stands as a testament to human ingenuity and the double-edged nature of technological progress. It was a machine that promised unlimited power but delivered uncontrollable danger. It showed what was possible when chemistry and engineering combined, but also revealed the limits of what society was willing to accept in pursuit of progress. Hermann Sprengel created something that was simultaneously a breakthrough and a dead end. A machine too powerful for its own good. The legacy of the Sprengel Explosive Engine reaches far beyond its brief and dangerous existence. While Hermann Sprengel's volatile creation never achieved commercial success, its influence ripples through modern technology in ways that would astonish its 19th century inventor. The engine's DNA lives on in rocket propulsion systems where controlled explosions still drive humanity toward the stars. Every time a spacecraft launches, every time a satellite adjusts its orbit, the fundamental principle remains unchanged. Explosive force precisely controlled, converted into forward motion. Modern rocket engines are essentially refined versions of Sprengel's concept. They mix fuel and oxidizer in controlled ratios, ignite the mixture in combustion chambers, and direct the explosive force through nozzles for maximum thrust. The difference lies in decades of engineering refinement, computer-controlled systems, and safety protocols born from hard-learned lessons. What Sprengel attempted with brass valves and mechanical timing, we now achieve with electronic fuel injection, thrust vectoring, and real-time monitoring systems. The engine's influence extends into the automotive world as well. Internal combustion engines operate on the same basic principle of controlled explosions driving pistons, though they use spark ignition rather than chemical detonation. The challenges Sprengel faced with timing, fuel mixture, and power delivery echo through every modern engine design. His struggles with valve timing prefigured the development of variable valve timing systems. His battles with fuel efficiency laid groundwork for direct injection technology. Even in military applications, the Sprengel engine's legacy persists. Modern explosive devices rely on principles Sprengel pioneered, mixing stable components that become violently reactive when combined. The engine's approach to harnessing chemical energy inspired everything from artillery shells to demolition charges. What was once a power source became a template for controlled destruction. The safety protocols developed in response to Sprengel's dangerous experiments became foundational to modern industrial practices. Every safety interlock, every emergency shutdown system, every hazardous material handling procedure traces its lineage back to the hard lessons learned from explosive engine failures. The engine's tendency to destroy itself taught engineers the critical importance of fail-safe design, redundant systems, and protective barriers. Perhaps most remarkably, the Sprengel engine anticipated modern concerns about energy density and instant power delivery. In an age increasingly focused on rapid charging, high-power batteries, and instant-on systems, Sprengel's vision of immediate, powerful energy seems almost prophetic. His engine could go from zero to full power in seconds, a capability that modern engineers still struggle to match safely and efficiently. The research techniques Sprengel employed also influenced scientific methodology. His systematic approach to testing different chemical combinations, his meticulous documentation of explosive properties, and his willingness to iterate through dangerous prototypes established patterns that explosive chemists still follow today. The engine project became a case study in how to push the boundaries of known science while attempting to maintain some measure of safety. Modern computational modeling allows engineers to simulate what Sprengel could only test through dangerous experimentation. Today's rocket designers can model combustion dynamics, pressure waves, and structural stresses before building physical prototypes. They can optimize fuel mixtures, chamber shapes, and cooling systems in virtual environments where explosions cause no harm. This represents the ultimate evolution of Sprengel's experimental approach, replacing physical danger with mathematical precision. The psychological impact of the Sprengel engine also deserves recognition. It captured imaginations in ways that conventional steam engines never could. The idea of harnessing explosions for everyday power generation struck people as both terrifying and thrilling. This emotional response to advanced technology prefigures modern reactions to everything from nuclear power to artificial intelligence. The engine taught society that transformative technologies often come with proportional risks. In educational contexts, the Sprengel Explosive Engine serves as a perfect example of how innovation requires balancing ambition with prudence. Engineering students study its design not just for its mechanical principles, but as a cautionary tale about the importance of safety margins, testing protocols, and risk assessment. The engine's failures became as instructive as its successes, perhaps more so. The materials science challenges Sprengel faced also resonate with modern engineering. His struggles with corrosion from nitric acid drove research into acid-resistant alloys and protective coatings. His problems with thermal expansion and contraction contributed to understanding of materials' behavior under extreme conditions. Every modern rocket engine benefits from metallurgy advances that trace back to problems first encountered in explosive engine development. Environmental considerations, largely ignored in Sprengel's era, now dominate discussions of explosive and combustion technologies. The toxic exhaust from his engine would be completely unacceptable today, but the challenge of managing combustion byproducts remains central to modern engine design. Clean combustion, emissions control, and environmental protection represent the evolution of concerns that explosive engines first raised. The Sprengel engine story also illustrates the unpredictable nature of technological development. What seemed like the future of power generation became an evolutionary dead end, while principles from the engine found new life in completely different applications. This pattern of unexpected technological migration continues today, as innovations in one field suddenly prove crucial in another. Looking forward, the Sprengel engine's emphasis on chemical energy storage and rapid power delivery may prove more relevant than ever. As renewable energy systems require better energy storage solutions, as electric vehicles demand faster charging, and as portable power systems need higher energy density, the core challenges Sprengel grappled with remain unsolved. His engine may have been ahead of its time, waiting for materials science and control systems to catch up. The Sprengel Explosive Engine stands as one of history's most fascinating technological paradoxes, a machine that embodied both the pinnacle of Victorian engineering ambition and the sobering reality of pushing boundaries too far, too fast. Hermann Sprengel's creation represented something far more significant than a mere mechanical curiosity. It was a glimpse into a future where controlled chemical explosions would become the backbone of modern civilization. When we examine the engine's impact through the lens of technological evolution, we see how its core principles became foundational to countless innovations that followed. The precise fuel injection systems that Sprengel pioneered evolved into the sophisticated injection technologies found in today's automotive engines, where computer-controlled timing ensures optimal combustion efficiency. The pressure management techniques developed for containing those violent chemical explosions laid groundwork for modern rocket engine designs, where similar principles propel spacecraft beyond Earth's atmosphere. Perhaps most remarkably, the engine's failure taught engineers as much as its successes. The catastrophic explosions and mechanical breakdowns that plagued Sprengel's device revealed critical insights about materials science, metallurgy, and safety engineering that would prove invaluable for future generations. Every cracked cylinder, every shattered component, every dangerous malfunction provided data that informed the development of safer, more reliable explosive-powered systems. The military applications that initially attracted attention to the Sprengel engine eventually manifested in ways Sprengel himself could never have imagined. Modern artillery systems, missile propulsion, and even demolition technologies all trace their lineage back to the fundamental principle of harnessing controlled chemical explosions for mechanical work. The engine's influence extended beyond direct military applications into the realm of industrial processes, where controlled explosions now shape everything from mining operations to manufacturing techniques. What makes the Sprengel engine's story particularly compelling is how it illustrates the unpredictable nature of technological progress. Sprengel's contemporaries dismissed his invention as too dangerous, too unreliable, and too impractical for widespread adoption. They weren't wrong. The engine was indeed all of these things. Yet their dismissal missed the deeper significance of what Sprengel had accomplished. He had demonstrated that chemical explosions could be tamed, controlled, and harnessed for productive purposes, even if the technology of his era wasn't sophisticated enough to do so safely. The economic factors that ultimately doomed the Sprengel engine also provide valuable lessons about innovation and market adoption. The high cost of specialized fuels, the expense of constant repairs, and the liability issues surrounding such a dangerous device created insurmountable barriers to commercialization. These same challenges continue to face modern inventors working with cutting-edge technologies, reminding us that technical brilliance alone isn't sufficient for commercial success. Modern environmental considerations add another layer to the Sprengel engine's legacy. The toxic chemicals it employed, nitric acid, benzene, toluene, would be considered environmental hazards by today's standards. Yet the engine's pursuit of efficiency and power output prefigured contemporary efforts to develop cleaner, more efficient propulsion systems. The fundamental challenge Sprengel faced, maximizing energy output while minimizing unwanted byproducts, remains central to modern green technology initiatives. The story of the Sprengel Explosive Engine ultimately serves as a powerful reminder that technological progress rarely follows a straight line. Innovations that seem like dead ends often contain seeds of future breakthroughs. The engine's apparent failure masked its true success, proving that controlled chemical explosions could power machines even if the materials and control systems of the 1870s weren't adequate to the task. Today, as we stand on the brink of new energy revolutions involving hydrogen fuel cells, electric propulsion, and advanced battery technologies, the Sprengel engine's legacy remains relevant. It reminds us that bold experimentation, even when it leads to spectacular failures, can illuminate paths toward future success. The engine's principles live on in every car engine, every rocket launch, every controlled demolition, and every industrial process that harnesses chemical energy for mechanical work. Today, as we stand at the forefront of revolutionary energy technologies, the Sprengel Explosive Engine reminds us that progress often emerges from the most unexpected and seemingly impractical ideas. Hermann Sprengel's audacious creation may have been too dangerous for its time, but it planted seeds that would eventually bloom into the sophisticated systems we rely on today. From the rocket engines that propel us to space to the internal combustion engines in our vehicles, the DNA of Sprengel's explosive innovation lives on. The engine's story teaches us that failure and success are often intertwined in the fabric of technological advancement. What appears as a dead end in one era can become the foundation for breakthrough innovations in another. The safety protocols developed in response to the engine's dangers continue to protect workers and communities worldwide, while its core principles of controlled chemical energy release remain fundamental to modern propulsion systems. As we face contemporary challenges in clean energy and sustainable transportation, the Sprengel Explosive Engine serves as both inspiration and warning. It encourages us to think boldly and push boundaries while respecting the immense forces we seek to harness. Innovation requires courage, but wisdom demands we learn from those who dared to experiment before us.